Evolving APIs, a practical guide to HATEOAS-driven REST. 1. The API landscape and the promise of REST. Welcome to the expansive and ever-evolving world of application programming interfaces, or APIs. In today's digital age, APIs are the invisible threads that weave together the fabric of modern software, enabling diverse applications, services, and devices to communicate and collaborate seamlessly. From booking an airline ticket to checking the weather on your phone, from microservices orchestrating complex business processes to smart home devices controlling your lighting, APIs are fundamental to how systems interact. They are, quite simply, the lingua franca of interconnected software. A brief history of API styles. The concept of programmatic interaction between distinct software components is not new. Early forms of APIs often involved tightly coupled communication protocols, such as remote procedure calls, RPC, in the 1970s and 80s. RPC allowed a program on one computer to execute a procedure or function on a remote computer, making it seem as if the function was being called locally. While powerful, RPC systems often led to brittle integrations, as changes to the remote procedure's signature could easily break the client. The turn of the millennium saw the rise of web services, primarily driven by SOAP, Simple Object Access Protocol. SOAP brought a more structured, XML-based approach to defining messages and interactions. It emphasized strict contracts, often verified by WSDL, Web Services Description Language, which provided a rigid blueprint for communication. While SOAP offered greater interoperability and formal standardization than RPC, its verbosity, complexity, and overhead often made it cumbersome for simpler integrations, particularly for the burgeoning web. The rise of REST. A promise half kept. Around the same time SOAP was gaining traction, a different architectural style began to emerge, one that drew inspiration from the very architecture of the World Wide Web itself. This was representational state transfer, or REST, first formally described by Roy Fielding in his 2000 doctoral dissertation. Unlike its predecessors, REST is not a protocol or a standard in the rigid sense, but rather a set of architectural constraints applied to distributed systems. The promise of REST was to create web services that were simpler, more scalable, and truly evolvable. At its heart, REST revolves around the concept of resources. Anything that can be named, whether it's a document, an image, a user, or an order, can be a resource. These resources are identified by Universal Resource Identifiers, URIs, the most common form of which are URLs, Uniform Resource Locators. Clients interact with these resources by exchanging representations of their state, often in formats like JSON or XML, using standard, uniform operations. Let's unpack the core architectural constraints that define a truly res-TFL system and distinguish it from many common interpretations. Client-server separation. This principle dictates that the client and the server should be distinct and independent. Each can evolve separately, as long as the interface between them remains consistent. This division of concerns improves portability and scalability. Statelessness. Crucially, the server holds no client context between requests. Each request from the client to the server must contain all the information necessary to understand the request, without relying on any stored session information on the server. This makes servers easier to scale and recover from failures. Cacheability. Responses from the server can, and should, be explicitly or implicitly marked as cacheable or non-cacheable. This allows clients or intermediaries, like proxies and gateways, to cache representations, reducing the need for repeated requests and improving overall performance. Layered system. A client may not be able to tell whether it is connected directly to the end server or to an intermediary. Intermediary servers, proxies, load balancers, gateways, can be introduced to enhance scalability, security, and performance without affecting the client-server interaction model. Uniform interface. This is arguably the most crucial constraint, and the one most often misunderstood or partially implemented. It simplifies the overall system architecture by ensuring that all interactions between client and server follow a common pattern. The uniform interface has 4 subconstraints. Identification of resources. Resources must be identifiable via URIs. Manipulation of resources through representations. Clients change the state of resources by sending representations. For example, sending a JSON body with an HTTP PUT request to update a user resource. Self-descriptive messages. Each message, request, or response must contain enough information for the recipient to understand how to process it. This typically involves using standard HTTP methods: GET, POST, PUT, delete, and media types, e.g., application/JSON, text/HTML. Hypermedia as the engine of application state, HATOAS. This is the constraint that most profoundly impacts the evolvability and dynamic nature of a res-TFL system, and it is the focus of this book. It means that clients navigate the application not by consulting out-of-band documentation or hard-coding URIs, but by following links provided within the responses themselves. The API responses don't just contain data, they contain instructions on what actions are currently available and where to go next. The elephant in the room: misconceptions of REST. Despite its elegance, the REST acronym has been widely adopted, often without a full understanding of its underlying architectural principles. Many APIs proclaimed as res-TFL only adhere to a few of the constraints, typically client-server, statelessness, identification of resources, and manipulation via representations and HTTP methods over JSON. While this style is undoubtedly simpler and often more practical than SOAP, it typically falls short of true REST by neglecting the uniform interfaces, self-descriptive messages, and, most significantly, hypermedia as the engine of application state. This common interpretation leads to APIs where developers often refer to them as res-TFL, but they are in fact simply HTTP-based JSON APIs. These APIs might expose resources like users, /orders/ed, or products. While useful, the client still needs prior knowledge to navigate them. To create an order, first post to orders, then get the details, then perhaps put to /orders/id/shipping. This knowledge is typically gleaned from external documentation, shared specifications, or even intuition. This implicit contract, relying on out-of-band information, is a primary source of fragility in many modern APIs. If the server changes a URI, or introduces a new step in a workflow, or deprecates an old endpoint, clients built with hard-coded assumptions inevitably break. Imagine if your web browser needed a separate software update every time a website changed a link or added a new form. This illustrates the fundamental elegance and power that HATOAS brings to the table. Just as a browser navigates the entire World Wide Web by simply following links and filling out forms, a HATOAS client interacts with an API without needing to know its precise URI structure beforehand. The API itself tells the client what it can do next. This book will guide you through understanding, designing, and implementing APIs that truly embrace the promise of REST, particularly its most powerful and often overlooked constraint, HATOAS. By the end, you'll be equipped to build APIs that are not just data providers, but engines of application state, capable of evolving gracefully and fostering truly adaptive client applications. 2. The challenge of evolving APIs: why we need HATOAS. In the previous chapter, we explored the foundational principles of REST and hinted at the critical role of hypermedia as the engine of application state, HATOAS. Now, let's confront the significant challenges that arise when APIs, even those claiming to be res-TFL, fall short of this crucial constraint. We'll illustrate the pain points that HATOAS is specifically designed to alleviate, setting the stage for its deep dive in the chapters to follow. The brittleness of traditional REST APIs. Imagine you're building a client application for an e-commerce platform. Your application needs to allow users to browse products, add them to a shopping cart, and then proceed to checkout. A typical HTTP-based JSON API might look something like this: get products, to retrieve a list of available products. Get /products/ID, to get details of a specific product. Post cart items, to add a product to the cart. Your client sends a product ID and quantity. Get cart, to view the current cart contents. Post checkout, to initiate the checkout process. This seems straightforward, right? But what happens when the API inevitably evolves? Client-server coupling. Your client application is intimately familiar with every URI path. It knows that to get product details, it must construct /products/id. It knows that to add an item to the cart, it must send a post request to cart items. If the API provider decides to change products to inventory or cart items to shopping basket additions, your client immediately breaks. These hard-coded URI paths create a tight, fragile coupling between client and server, making independent evolution nearly impossible. Every server change risks a client redeployment, sometimes across hundreds or thousands of distributed clients. Lack of discoverability. How does your client know about products, cart items, or checkout in the first place? It learns this knowledge out of band. This means the information is not provided by the API itself, but comes from external sources like documentation, a static page describing endpoints and their parameters, shared specifications, OpenAPI, Swagger, or Postman collections, verbal communication, the API developer telling the client developer, implicit knowledge, assuming a GET users will list users. This means your client isn't truly discovering the API's capabilities. It's simply executing predefined instructions. When new actions become available, e.g., apply coupon, track order, the client needs to be explicitly updated to incorporate these new, hard-coded behaviors. Implicit workflows. Consider the e-commerce checkout process. The flow is usually add items to cart, view cart, initiate checkout, confirm payment, get order confirmation. In non-HATEOAS APIs, your client application is responsible for knowing and enforcing this sequence. It might look something like this. Client-side pseudocode. Function checkout process. If cart is empty. Display message, cart is empty, please add products. Return. Step 1, initiate checkout. Send post request, /checkout, cart data. Assuming success, then client knows too. Step 2, confirm payment. Send post request, /payment confirmation, payment data, and so on. The client explicitly manages the application state. What step comes next? If the server introduces an intermediary step, say, a shipping address confirmation before payment, the client's hard-coded workflow breaks. The API isn't guiding the client through the process. It's merely responding to predefined requests. Version management headaches. Because APIs are so tightly coupled to their clients, developers frequently resort to API versioning, e.g., api.example.com/v1/products, then v2 products. This is an attempt to manage breaking changes. However, versioning doesn't eliminate the problem. It simply slows down the breaking changes and introduces its own set of complexities. Servers must maintain multiple versions of their API, increasing maintenance burden. Clients must explicitly state which version they are using. Updating clients to new versions can still be a significant effort, even if the old version remains temporarily available. It's a temporary patch, not a long-term solution for API evolution. Maintenance nightmares. The sum of these challenges is a significant increase in the operational overhead and cost of maintaining APIs and their dependent clients. Every change, even minor ones, can ripple through the entire ecosystem, demanding coordination, testing, and redeployment across multiple teams and services. The engine of application state problem. The fundamental issue is that many APIs provide data, but they don't provide the context or guidance necessary for the client to truly drive the application. The client implicitly manages the application's workflow and state. It makes decisions based on assumptions about valid next steps or available operations, rather than receiving that guidance directly from the server. Consider a simple, everyday analogy. Imagine you're trying to use a vending machine. A non-HATEOAS vending machine would just have a single, static button labeled dispense. You'd have to know, from an external manual or prior experience, that you first need to insert coins, then type a product code, and then press dispense. If the machine runs out of change, or a particular product, it just gives you an error when you try to dispense, and you're left guessing why. A HATEOAS vending machine would be much more intuitive. When you approach it, it might display Insert Coins. Once you insert coins, It might then show you a list of available products with their prices, along with a Select Product button for each. If a product is out of stock, that Select Product button wouldn't appear. If you insert enough money, then a Dispense button might light up, or a Get Change button if you've overpaid. The machine itself is the engine of your application state, guiding you step by step through the process, indicating what you can do right now. You don't need a manual because the machine tells you what's possible, and the options change dynamically based on the current state. This is precisely the promise of HATEOAS in the API world. The server, knowing the current state of a resource and the user's permissions, dynamically exposes the valid next actions and their associated URIs directly within the API response. The client doesn't need to hardcode a complex workflow or specific URIs. It simply reads the available links and hypermedia controls from the server's response and dynamically decides its next step. Introducing the promise of HATEOAS. By embracing HATEOAS, we move away from brittle, hard-coded integrations towards a more resilient and flexible architecture. The benefits are profound: reduced client-server coupling. Clients no longer hard-code URIs or workflow sequences. They discover them at runtime, making them more resilient to server-side changes. Enhanced discoverability. The API itself becomes self-descriptive. A client can browse the API, much like a human browses a website, by following links and discovering new capabilities as they are exposed. Dynamic workflow guidance. The server dictates the valid transitions and actions, guiding the client through complex business processes. The presence or absence of a link or an action directly informs the client about what can or cannot be done at a given moment. Graceful evolution. When the API changes, e.g., a new step is added to a process, an existing resource's URI changes, or new functionality is introduced. Existing clients that are truly HATEOAS-driven are far less likely to break. As long as the semantics of the link relations remain consistent, the client can adapt without being redeployed. New links simply appear and can be leveraged by updated clients, while old clients can continue to use the links they understand. The adoption of HATEOAS transforms APIs from mere data endpoints into dynamic, self-navigating systems. It is the architectural constraint that truly unlocks the evolvability that REST was designed to provide. In the next chapter, we will decode HATEOAS, examining its core components and how they fit together to fulfill this powerful promise. 3. HATEOAS Decoded: Core Principles and Concepts. In the previous chapter, we established the critical need for HATEOAS by demonstrating the fragility and limitations of APIs that neglect this fundamental REST constraint. Now, it's time to pull back the curtain and fully decode HATEOAS. We'll explore exactly what it means for an API to be an engine of application state and delve into its core components: resources, links, and hypermedia controls. Defining HATEOAS. Hypermedia as the engine of application state. Let's break down the acronym, hypermedia. Simply put, hypermedia refers to media, like text, images, video, that contain links to other media. On the web, HTML documents with their href equals. Tags are the quintessential example of hypermedia. In the context of APIs, hypermedia means that the data returned by the API is interspersed with links that point to related resources or available actions. As the engine of application state, this is the profound part. It means that the client application, instead of relying on pre-programmed knowledge of URIs and workflows, discovers its capabilities by following the links present in the hypermedia. The server dictates what the client can do next by providing or withholding relevant links. The state here is not just the data within a resource, but the application's workflow state. What actions are possible from the current point? Consider the vending machine analogy again. The machine server presents you with text, insert coins, then perhaps a list of products, data, along with buttons, select Pepsi, select Coke. These buttons are the hypermedia. The machine then guides you from insert coins state to product selection state, and then dispense state, driving the application's flow via the available choices. An API that truly adheres to HATEOAS effectively becomes a self-documenting, self-discovering system. A client needs only a single, well-known entry point URI. And from there, it navigates the entire API by dynamically interpreting the links and controls presented in each response. Key components of HATEOAS. To achieve this dynamic state transition, HATEOAS APIs rely on a few crucial building blocks. 1. Resources and representations. As we discussed, everything in REST is a resource. A resource might be a user, an order, a product, or even a shopping cart. When a client requests a resource, the server sends back a representation of that resource's current state. This representation is typically a JSON or XML document, though it can be anything from an image to a PDF. The key in HATEOAS is that this representation doesn't just contain raw data. It also contains links and controls that are relevant to that resource at its current state. Example, a pending order resource. Let's imagine a simplified JSON representation of an order. Ordered, ORD123. Status, pending. Total amount, 100.00. Currency, USD. Customer name, Alice Smith. Other data. This is data. A HATEOAS representation will add hypermedia. Ordered, ORD123. Status, pending. Total amount, 100.00. Currency, USD. Customer name, Alice Smith. Links, self, href, orders ORD123. Customer, href, customers CUSD 456. Add item, href, orders ORD123 items. Cancel, href, orders ORD123 cancel. Now the client sees not just the order data, but also what actions are available, add item, cancel, and how to get related resources, customer, or the current resource's canonical URI, self. 2. Links. Links are the fundamental navigators in a HATEOAS API. They connect resources and indicate possible transitions or related information. A link typically consists of URI, Uniform Resource Identifier. This is the actual address or location of the related resource or action. For example, orders ORD123 items. In some cases, URIs can be parameterized using URI templates defined by RFC 6570, which allow for variables within the URI path or query string. For instance, /products, category, min price indicates that a client can query products by category and minimum price. The client fills in these template variables. Link relation, rel. This is perhaps the most crucial part of a HATEOAS link. The rel describes the purpose or meaning of the link. It defines the semantics of the relationship between the current resource and the linked resource. Instead of hard-coding orders ORD123 cancel, the client looks for a link with the relation cancel. If the URI for canceling an order ever changes, the client doesn't break, as long as the rel equals cancel link is still present and points to the new URI. Link relations can be standard relations. Many common relations are registered with the Internet Assigned Numbers Authority IANA Link Relation Registry. Examples include self points to the URI of the current resource. Next, prev, first, last, used for pagination. Collection points to a resource that is a collection of the current resource's type. Item points to an individual item within a collection. Custom domain-specific relations. For operations unique to your domain, you can define your own link relations. Good custom relations are verbs or verb phrases that clearly describe the action or relationship, e.g., add item, confirm order, apply discount, track shipment. It's critical that these custom relations are well documented for clients to understand their meaning. Optional attributes. Links can include other attributes to provide more context, such as title, a human-readable title for the link. Name, a common identifier for the link or the resource linked to. Type, hints about the media type of the resource to be. Retrieved, e.g., application/JSON. Templated, a Boolean indicating if the href is a URI template. When a client receives a response, it doesn't parse the URI string directly. Instead, it inspects the link relations to determine what operations are available. This fundamental shift in client programming is what makes HATEOAS so powerful for evolvability. 3 hypermedia controls, forms. While links are excellent for GET requests, navigating to resources, they are not sufficient for operations that require data submission, like post, PUT, delete, or patch. For these, HATEOAS introduces the concept of hypermedia controls, often referred to as forms or actions. These controls provide the client with the href target URI for the action, the HTTP method to use post, PUT, delete, etc., a description of the fields or parameters required for the action, e.g., name, type, value, required, pattern. This allows the client to dynamically construct a request body or URL parameters. Example, a confirm order action for a pending order. Using a hypermedia format like Siren, which we'll cover in Chapter 4, our pending order might include an action. Class, order. Properties, ordered, ORD123. Status, pending. Total amount, 100.00. Links, rel, self, href. Orders ORD123. Actions, name, confirm order. Title, confirm order. Method, post. href, orders ORD123 confirm. Type, application/JSON. Fields, name, confirmation code, type, text, title, confirmation code. Now, the client knows that to confirm an order, it should perform a post request to orders ORD123 confirm and include a confirmation code field in the request body. The client doesn't need to be hard-coded with this path or the specific field name. It discovers them directly from the API response. Application state versus resource state. It's crucial to distinguish between resource state and application state. Resource state, this is the current data of a specific resource, e.g., an order being pending, a user being active. Application state, this refers to the overall progress of the client application through a workflow or process. HATEOAS manages the application's workflow state by dynamically providing links and controls that are relevant to the current resource state and available to the current user. When the order status changes from pending to confirmed, the API response for that order will no longer include the cancel or add item links, but perhaps a track shipment link. The absence or presence of these links guides the client through the application's lifecycle, implicitly indicating valid transitions. Discoverability in practice and the evolvability benefit. With HATEOAS, a client typically starts at a well-known root URI, like /API/. From there, it receives a set of links. It might follow a customer's link to get a list of customers, then a self-link for a specific customer, and then a create order link associated with that customer. This dynamic discovery of capabilities means reduced breaking changes. If the server changes the underlying URI scheme, e.g., customer's CUSD123 orders becomes client's CUSD123 purchases, as long as the link relation, e.g., customer orders, remains consistent, the HATEOAS client will not break. It will simply follow the link provided by the server, regardless of the URI's structure. Backward compatibility. New capabilities can be introduced by simply including new links or actions in responses. Older clients, not programmed to understand these new relations, will simply ignore them, continuing their existing workflows without breaking. Newer, updated clients can leverage the new functionality seamlessly. Simplified client logic. Complex workflow logic shifts from the client to the server, where it belongs. The client's role becomes primarily about presenting available options to the user and executing actions based on the hypermedia controls it receives. In essence, HATEOAS elevates the API from a simple data provider to an active participant in guiding the client application. It breathes true life into the REST architectural style, making systems more robust, flexible, and evolvable. In the next chapter, we'll dive into the specifics of popular hypermedia formats like HAL and Siren, showing how these abstract concepts are concretely implemented. 4. Understanding hypermedia formats. HAL, Siren, and beyond. In the previous chapter, we dissected the core concepts of HATEOAS, resources embedded with links and hypermedia controls. But how are these theoretical constructs actually represented in the raw data exchanged between clients and servers? This is where hypermedia formats come into play. Just as we use JSON or XML to serialize data, we use specific hypermedia formats to structure the data, links, and forms within an API response. The choice of hypermedia format is critical. It impacts the ease of implementation on both the server and client, the expressiveness of your API, and ultimately, its adoptability. While there are many formats, we'll focus on a few prominent ones, highlighting their strengths, weaknesses, and ideal use cases. Why standards matter. Before diving into specific formats, it's worth pondering why standardization is important. A widely adopted standard brings consistency. Developers don't have to relearn how links are represented for every new API. Tooling support. Libraries and frameworks can be built to parse and generate these formats, simplifying development. Interoperability. Different systems can more easily communicate if they agree on the common structure for hypermedia. Now, let's explore some of the leading contenders. 1. HAL, Hypertext Application Language. HAL is arguably the most widely adopted and simplest hypermedia format. Its strength lies in its minimalism and ease of understanding, making it an excellent starting point for HATEOAS adoption. HAL specification is deliberately concise, defining just two primary reserved properties within a JSON or XML document: links and embedded. Key concepts of HAL: links. This property holds all the links associated with the current resource. It's an object where each key is a link relation, e.g., self, customer, next, create order, and its value is either a link object or an array of link objects, if multiple links share the same relation. A link object typically contains href, the URI of the target resource. Rel, the link relation name. This is also the key in the links object. Templated optional, a boolean indicating if href is a URI template. Type optional, hints about the media type of the target resource. Name, title, profile, hreflang optional, additional metadata. Embedded, this property allows related resources to be embedded directly within the current representation. This reduces the number of HTTP requests a client needs to make, improving performance. Like links, it's an object where each key is a link relation, describing the relationship of the embedded resource to the current one, and its value is either a single embedded resource object or an array of embedded resource objects. HAL example. Let's revisit our order resource, formatted in HAL. Ordered, ORD123. Status, pending. Total amount, 100.00. Currency, USD. Customer name, Alice Smith. Links, self, href, orders ORD123. Customer, href, customers CUSD 456. Add item, href, orders ORD123 items. Templated, true. This link might expect a product ID and a query param. Cancel, href, orders ORD123 cancel. Embedded, customer, customerid, CUSD 456. Name, Alice Smith. Email, alice@example.com. Links, self, href, customer CUSD 456. Pros of HAL: simplicity, very easy to understand and quick to implement, reduces boilerplate, concise, doesn't add much overhead to existing JSON responses, widespread adoption, many libraries and tools exist for HAL parsing generation. Cons of HAL: limited action form support. HAL itself doesn't define a standard way to represent hypermedia controls, forms, beyond simple links. While extensions, like HAL forms, exist, they are not part of the core HAL specification and lead to fragmentation. This means for post-PUT operations, you might still rely on out-of-band documentation for body structure. Verbosity for multiple rels. If a resource offers many links, the links section can become quite large. 2. Siren. Siren is a more opinionated and feature-rich hypermedia format, designed with a stronger emphasis on guiding client interactions, particularly for complex workflows involving actions and fields. It sees a resource as an entity and explicitly supports actions that clients can perform. Key concepts of Siren: class, an array of strings that describe the nature of the entity, useful for client-side routing or styling. Properties: the data of the entity, similar to a standard JSON object. Links, similar to HAL, an array of link objects. Each link object has a rel array of strings, href, and optional type and title. Actions. This is where Siren truly shines. It's an array of objects describing available actions that can be performed on the entity. Each action includes name, a unique identifier for the action; href, the URI where the action should be sent; method, the HTTP method, e.g. post PUT; fields, an array of objects describing the input fields required for the action, name, type, value, optional placeholders; type, the media type of the submission, e.g. application/JSON; entities, similar to HAL's embedded, this allows embedding related entities directly. Siren embedded entities can also be subentities, structured via rel and href, or represented as part of an aggregate, structured via class. Siren example. Let's represent our pending order in Siren, including a confirm order action. Class, order. Properties, ordered, ORD123. Status, pending. Total amount, 100.00. Currency, USD. Customer name, Alice Smith. Links, rel, self, href, orders ORD123. Rel, customer, href. Customer CUSD 456. Actions, name, add item. Title, add item to order. Method, post. Href, orders ORD123 items. Type, application/JSON. Fields, name, producted, type, text, title, product ID. Name, quantity, type, number, title, quantity, value, 1. Name, confirm order. Title, confirm order. Method, post. Href, orders ORD123 confirm. Type, application/JSON. Fields, name, confirmation code, type, text, title. Confirmation code. Name, cancel order. Title, cancel order. Method, delete. Href, orders ORD123 cancel. Entities, class, customer. Rel, customer. Properties, customerid, CUSD 456. Name, Alice Smith. Email, alice@example.com. Links, rel, self, href. Customer CUSD 456. Pros of Siren: strong action form support. Excellent for complex workflows that require client input, making clients truly dynamic. Expressive: clearly defines what actions can be taken and what inputs they require. Well-defined structure, less ambiguity than more minimal formats. Cons of Siren: more complex, greater learning curve for developers compared to HAL. More verbose, can lead to larger response payloads than HAL due to richer structure. 3. Collection plus JSON. Collection plus JSON is a hypermedia format specifically designed for reading and writing collections of resources. It simplifies common API patterns like listing items, querying, and adding new items to a collection. It's less general purpose than HAL or Siren for single resource representations, but excels in scenarios where you're primarily dealing with lists of things. Key concepts of collection plus JSON. Collection, the root object containing, version, current version of the format. Href, the URI of the collection itself. Links, global links for the collection, e.g. pagination links. Items, an array where each element represents a resource within the collection. Each item has href, the URI of the item. Data, an array of name-value pairs representing the item's properties. Links, links specific to that item. Queries, an array describing how to filter or sort the collection, akin to search forms. Each query has a href, rel, and data fields for input. Template, this is a crucial feature for adding new items to the collection. It defines the structure and fields required for a post operation to the collection's href. Collection plus JSON example for a collection of orders. Collection, version 1.0. Href, orders. Links, rel, next, href, /orders page equals 2. Rel, search, href, /orders status, templated, true. Items, href, orders ORD123. Data, name, ordered, value, ORD123. Name, status, value, pending. Name, total amount, value, 100.00. Links, rel, customer href, customer CUSD 456. Rel, details, href, orders ORD123 details, link to full details. Href, orders ORD 456. Data, name, ordered, value, ORD 456. Name, status, value, shipped. Name, total amount, value, 250.00. Links, rel, customer, href, customer CUSD 789. Queries, rel, search by status, href, orders, data, a name, status, value, pending. Template, data, name, customer-id, value, name, items, value, name, currency, value, USD. Pros of collection plus JSON, specialized for collections, excellent for common patterns like listing, searching, and creating items in a collection. Built-in query support. The queries and template properties handle common scenarios elegantly. Cons of collection plus JSON. Less general purpose. Not ideal for representing single resources that aren't part of a collection or for complex stateful workflows of a single entity. Verbose for simple data. The data array of name-value pairs can be more verbose than a simple JSON object for properties. Beyond, JSON, API, UBER, Mason. JSON, API. While it includes a links object, JSON, API is primarily an opinionated specification for building APIs that aims to reduce requests and provide strong caching. Its focus is more on serialization structure and relationship fetching rather than dynamic workflow guidance through arbitrary link relations like full HATEOAS. It's often used with client-side frameworks that prefer predefined data structures. UBER, uniform basis for exchanging representations. A minimal alternative to HAL, focusing on simplicity by defining only two concepts, URI and REL. It can result in very lean representations, but might require more client intelligence. Mason, a comprehensive and flexible hypermedia format that includes strong support for forms, alerts, and metadata, making it highly suitable for rich client interactions. It shares some conceptual similarities with Siren, but offers even more features. Choosing the right format. The choice of hypermedia format depends heavily on your specific needs. For simple APIs and general-purpose resource linking, HAL is an excellent choice due to its simplicity and broad adoption. You might augment it with a separate, informal convention for forms if your workflows are simple. For APIs that drive complex, stateful workflows requiring dynamic user input, Siren or Mason provide the necessary expressiveness through their rich action form capabilities. These are powerful for building truly adaptive clients. For APIs that primarily manage collections of resources, e.g., CRUD-heavy lists and searching, Collection plus JSON might be a very efficient and clean solution. It's also possible to use different hypermedia types for different parts of your API if that provides the best fit, leveraging content negotiation, which we'll touch on in Chapter 10. However, consistency generally makes clients easier to build. Understanding these formats is the first step towards implementing HATEOAS-driven APIs. Now that we've seen how hypermedia can be structured, the next chapter will dive into the art of designing your API resources and link relations to maximize discoverability and evolvability. 5. Designing discoverable APIs, resource modeling and link relations. Having covered the why and the what of HATEOAS, we now turn to the how. This chapter is about the design process itself. How do you envision your API resources so they embrace hypermedia? And how do you define the links and actions that will make your API truly discoverable and evolvable? This isn't just about technical implementation. It's about shifting your mindset from data-centric to behavior-centric API design. Resource modeling in a hypermedia context. Traditional API design often starts with data schemas or database tables. You might have a user table, an order table, a product table, and then create corresponding users, orders, products, endpoints. While this provides data, it doesn't necessarily reflect the business capabilities or application states your API needs to manage. In a hypermedia context, your resources should represent meaningful business concepts, and their representations should reveal not just their data, but also what actions can be performed on them and what related concepts exist. Think less about tables and more about things users interact with or stages of a business process. Key principles for resource modeling. Focus on business entities' aggregates. Instead of exposing granular database rows, model your resources around coherent business aggregates. For example, an order might contain order items, shipping address, and payment details as intrinsic parts of its representation, rather than requiring separate API calls for each. Identify state and life cycle. Most business entities have a life cycle, e.g., order goes from pending to confirmed to shipped. Your resource representations should clearly indicate their current state, as this dictates which links and actions are available. Think verbs as links actions. Identify the core actions a client would want to perform on a resource or related to it. These verbs often translate directly into link relations or hypermedia actions. For an order resource, cancel order, confirm order, add line item, track shipment. For a product resource, add to cart, view reviews. For an invoice, pay invoice, dispute invoice. Defining link relations. The heart of discoverability. Link relations, the rel attribute, are the most critical aspect of your HATEOAS APIs contract. They define the semantics of the relationship or action. A client doesn't care where add item points, only that it can add an item and what it needs to add an item. Standard versus custom relations. Standard IANA relations. Always prefer standard relations when they exist and logically fit your use case. This promotes consistency and leverages existing tooling understanding. Common examples include self, the URL of the current resource. Next, prev, first, last, for pagination. Up, the collection that contains the current resource. Item, an individual item in a collection. Collection, a resource that is a collection. Canonical, the preferred version of a resource. Authenticate, authorize, for security-related links. You can find a comprehensive list and their definitions at the IANA Link Relations Registry. Custom domain-specific relations. When no standard relation accurately describes the relationship or action, you must create a custom one. Naming conventions. Be descriptive and semantic. The rel name should clearly convey the purpose. Avoid vague terms. Kebab case. Use kebab case for multi-word relations, e.g., add to cart, confirm payment. Lowercase. Keep it simple and consistent. Avoid URIs for names. While the spec allows full URIs as relation names, e.g., http://relations.example.com/payment. For practical purposes, short, descriptive names are typically preferred unless you're building a highly federated system across many different organizations. Follow established patterns. If your domain has common terms for actions, e.g., approve, reject, use them. Good examples of custom relations: place order, cancel reservation, track shipment, apply discount, upload document, approve application, add review. Bad ambiguous examples: process, what process, action, what action, update, what is being updated, which fields. Important: when you define custom link relations, you are creating a contract. These relations implicitly tell the client what kind of behavior to expect. Any client using your API will rely on the meaning of these relation names being stable. You must document their meaning clearly. Using URI templates, RFC 6570. Sometimes a link needs parameters that the client provides. Instead of returning a full, prefabricated URI with default parameters, which limits flexibility, you can return a URI template. This tells the client how to construct the final URI. Example, a relation search for products. Instead of href/products query equals laptop and min price equals 0, too specific. Use a URI template. href/products query min price max price, templated, true. This indicates to the client, here is a link to search products. You can provide query, min price, and max price as query parameters. The client library can then easily fill in these parameters. Structuring representations, weaving and hypermedia. The way you embed links and actions within your resource representations significantly impacts clarity and usability. Links for related resources. Use links to point to other resources that are related but not necessarily embedded. Example: an order resource might link to its customer and the products it contains, but not embed full customer or product details unless specifically requested to avoid excessive payload size. Links for actions transitions. Use links for simple GET navigations or to initiate a new resource lifecycle, e.g., a payment link that takes you to a payment resource. For more complex actions requiring input non-get, use hypermedia controls forms like Siren's actions. Embedding related resources embedded in HAL. While links promote discoverability, sometimes the client almost always needs related data immediately. Embedding can reduce round trips. When to embed, the related resource is small. It's frequently accessed with the parent resource. The embedded data is unlikely to change independently very often. It significantly reduces chatty client-server communication. When not to embed, the related resource is large, e.g., a list of all historical orders for a customer. It changes frequently and independently. The client needs to act on the embedded resource separately. In these cases, provide a link and let the client explicitly fetch it if needed. Good rule of thumb: embed if it makes sense to retrieve it every time the parent is retrieved. Otherwise, link, guiding workflow with links, state transitions in practice. This is where the magic of HATOAS truly shines. The availability of links and actions changes based on the resource's current state and the contextual business logic. Example: order lifecycle. New order just created. Status pending. Links: self href. Orders ORD 123. Add item href. Orders ORD 123 items templated true. Confirm href. Orders ORD 123 confirm. Cancel href. Orders ORD 123 cancel. The client sees it can add items, confirm or cancel. Confirmed order. If the order is confirmed, adding items or canceling might no longer be allowed. Status confirmed. Links: self href. Orders ORD 123. Track shipment href. Shipments XYZ 456. View invoice href. Invoices INV 789. The client now sees different options: track shipment, view invoice. The previous links are gone because the actions are no longer valid for this state. The client does not need to know the state machine. The API directs it. This dynamic response means client code can be simpler and more adaptive. It checks for the presence of a rel, e.g., confirm, rather than checking if order status == pending. Hypermedia controls forms actions beyond get. For operations like creating, updating, or deleting resources that involve submitting data, links alone are insufficient. This is where hypermedia controls, as seen in Siren, or HAL forms if you choose to extend HAL, become vital. When designing these forms, define required fields. Clearly specify the name, expected type, string, number, Boolean, date, and any validation rules min-max length, regex, enum values. Provide default value suggestions. If possible, offer sensible defaults or hints, e.g., for a country code field, suggest US. Indicate method. Explicitly state the HTTP method, post, PUT, delete, patch to be used. Specify media type. Indicate the content type for the request body, e.g., applications/JSON. Example: conceptual form for add item. Actions: name, add item. Method, post. href. Orders ORD 123 items. Type, application/JSON. Fields: name, producted, type, string, required, true, title, product identifier. A name: quantity, type, number, default, 1 min, 1 title, quantity of item. This tells the client that to add an item, it needs to post to orders ORD 123 items with a JSON body containing producted and quantity. Designing for evolvable APIs. The ultimate goal of HATOAS is evolvability. Keep these principles in mind during design. Stable link relations. While URIs can change, the meaning, semantics of your link relations should be stable. This is your core contract with the client. Don't over-optimize for embedding, resist the urge to embed everything. Provide links to related resources, allowing clients to fetch them only when needed. Think about the entry point. Your API will have one or a few well-known root URIs. Ensure these root resources provide meaningful links to major segments of your API, e.g., /API might link to customers, orders, products. Layer data and hypermedia. Clearly separate the resource data from its hypermedia controls within your representation. Designing truly discoverable HATEOAS APIs requires a shift in perspective. It's not just about exposing data, but about guiding interaction and making the API's capabilities explicit within its responses. By carefully modeling resources and defining meaningful link relations and hypermedia controls, you create an API that is not only robust, but also inherently adaptable to future changes. In the next chapter, we will transition from design principles to practical server-side implementation strategies for generating these rich hypermedia responses. 6. Server-side implementation patterns for HATEOAS. With the theory of HATEOAS and the principles of design firmly established, it's time to get practical. This chapter focuses on how to actually build a HATEOAS-driven API on the server side. While we won't delve into specific programming language code, we'll discuss the common patterns, architectural considerations, and strategies for dynamically generating HATEOAS responses regardless of your chosen framework. Choosing a hypermedia format, revisited. Before writing any code, confirm your choice of hypermedia format. As discussed in Chapter 4, the choice between HAL, Siren, collection plus JSON, or others will dictate the structure of your responses and, consequently, your implementation strategy. HAL, minimal and straightforward. Implementation involves adding links and embedded properties. Many frameworks have helper libraries for HAL. Siren, more complex due to actions and entities, requires more intricate generation logic for fields and action metadata. Collection plus JSON, specific patterns for items, queries, and template. Your implementation patterns will largely revolve around how you populate these specific sections within your chosen format. Generating links dynamically. The core of a HATEOAS server is its ability to generate context-aware links. This means the links served to the client must reflect the current state of the resource. As an order progresses from pending to shipped, the available actions, and thus links, change. The client's permissions role. A regular user might see a view profile link, but an administrator might also see an edit user or deactivate user link. The API's current business logic. If a product is out of stock, the add to cart link should not be present. Pattern 1, state-driven link generation. This is the most common and powerful pattern. Your application's domain model, e.g., order object, inherently has states. Based on these states, you attach relevant links. Domain object enhancers, conceptual. Imagine a component or method that takes a domain object, e.g., order, and its current state details. This component then consults a collection of rules or a state machine definition to determine which links are valid and adds them to the API representation. Conceptual logic for order resource. Function generate order links order. Let links equals, link self equals href, /orders $order ID. Always include self. If order status equals pending, links add item equals href, /orders $order ID /items, links dot confirm equals href, /orders $order ID /confirm, links dot cancel equals href, /orders $order ID /cancel. Else if order status equals confirmed, links track shipment equals href, shipment sorter shipmented, links generate invoice, href, invoices ordered, and so on for other states. Return links. Return these links to be embedded in the response. Benefits. This approach centralizes the logic for link generation, making it easy to see which links are possible for a given resource state. It directly supports the engine of application state principle. Pattern 2, role permission-based filtering. Beyond resource state, user permissions often determine available actions. Authorization interceptors processors. After generating the initial set of links based on resource state, pass these links through an authorization layer. This layer checks the current user's roles or permissions against each potential link action. If the user is not authorized for a particular action, that link is simply omitted from the response. Conceptual logic for access control. Function filter links by permissions, links, current user. Let filtered links equals. For const rel in links, if is authorized, current user, links rel, action purpose. Action purpose is a conceptual metadata. Filtered links rel equals links rel. Return filtered links. Benefits. Ensures security by only exposing actions a user is allowed to perform, rather than relying on the client to hide unauthorized UI elements. Avoiding hard-coded URLs. Resource lookup routing. Crucially, never hard-code URIs within your server-side code when generating links. Instead, leverage your framework's routing or resource lookup mechanisms. Named routes resource builders. Most web frameworks like Spring, Rails, Django, Express allow you to name routes or define methods for building URIs based on resource identifiers. Bad hard-coded. Link self equals href. Orders plus order getted. Good, using a conceptual route builder. Assuming order resource builder knows how to construct URIs for orders. Link self equals href. Order resource builder get URI, order get ID. Links customer equals href. Customer resource builder get URI, order get customer ID. Links.cancel equals href. Order resource builder get cancel URI, order get ID. Benefits. If you ever change your URI structure, e.g., from /orders/ID to /ecommerce/sales/ID, you only need to update your route definitions or resource builders, not every piece of code that generates a link. Embedding resources, embedded in HAL, entities in Siren. Embedding related resources can significantly reduce the number of HTTP requests a client needs to make. Conditional embedding. Don't embed everything by default. Consider size. Is the embedded resource small? Usage frequency. Is it almost always needed when the parent resource is fetched? Cohesion. Is it logically part of the parent's aggregate? For example, embedding the customer object within an order might make sense if customer details are frequently needed without a separate lookup. Embedding a list of all products from an order might not be, especially if there are many. Embedded versus links decision. If you choose to embed, ensure the embedded resource itself is a valid HATEOAS representation, i.e., it should also have its own self-link and any relevant other links actions. Always provide a link to the embedded resource even if you embed it. This allows clients to fetch the resource directly if they need a more detailed representation or if they need to bypass caching. Implementing hypermedia controls, forms actions. This is more involved, particularly with formats like Siren that have rich action definitions. Action definition objects. Create objects or classes that represent each possible action form. These objects would contain name, title, method, href, type, media type for the request body. A list of fields, each specifying name, type, required, value, and title. Dynamic field generation. Validation rules. The server should not just tell the client what fields are needed, but also how they should be validated. This can include min, max, pattern, regex, enum list of allowed values. Default values. Provide default values for optional fields. Context-specific fields. The fields exposed for an action might change based on the resource state. For instance, an update profile action might only allow updating certain fields if the user is not an administrator. Conceptual logic for populating an add item action. Function get add item action, order ID. Let action equals name, add item, title, add item to order. Method, post, href, /orders $order ID /items. Type, application /JSON. Fields, dynamically add fields based on product availability or other rules. Action fields push, name. Producted type string required true, action fields push. Name, quantity type number default 1 min 1, return action. Server-side validation. Remember that relying on the client to respect the fields and validation rules exposed in a hypermedia control is not enough for security. always performs server-side validation of incoming requests. The hypermedia control is a convenience for the client, not a security guarantee. Statelessness and session management. HATEOAS inherently supports REST's stateless constraint. Each client request carries all the necessary information, and the server's response provides all the necessary links for the next step. No server-side sessions. Avoid storing client-specific session data on the server between requests. All context needed to generate links or process requests should come from the request itself, e.g., authenticated user, request body, query parameters, URI path. Token-based authentication, e.g., JWT. For authentication and authorization, token-based approaches, like JSON web tokens, are perfectly suited. The token, sent with each request, implicitly carries user identity and permissions, which the server can use to conditionally generate links. Error handling in HATEOAS. Even HATEOAS APIs will encounter errors. When they do, the error response itself can be hypermedia-driven. Standard HTTP status codes. Continue to use appropriate HTTP status codes, e.g., 400 bad request, 401 unauthorized, 403 forbidden, 404 not found, 500 internal server error. Error details with links. Provide meaningful error messages and, where appropriate, include links to help the client rectify the situation or get more information. Code HATEOAS-driven Message. Product with ID P123 is currently out of stock. Links. Browse other products, href, products. Notify when available, href. Products P123 notify stock. Instead of just an error, the client is given actionable links. Conceptual architecture for HATEOAS server. A typical HATEOAS server flow might look like this. Request reception. Client sends an HTTP request. Authentication and authorization. Identify the user and their permissions. Resource retrieval operation. Fetch or process the requested resources from the backend database, other services. State identification. Determine the current business state of the resources. Link action generation. Based on the resource's state and the user's permissions, dynamically generate the relevant links and hypermedia actions. Representation assembly. Construct the full hypermedia response, e.g., HAL plus JSON, Siren plus JSON, including resource data, generated links, embedded resources, and actions. Response delivery. Send the hypermedia response to the client. Implementing HATEOAS on the server side requires careful thought about how your business logic, state, and permissions translate into dynamically generated links and forms. By adopting these patterns, you can build APIs that are not just data providers, but true navigators for your client applications, empowering them to adapt and evolve alongside your API. The next logical step is to explore how clients can effectively consume these intelligent API responses. 7. Consuming HATEOAS APIs, building robust clients. We've explored the why and how of designing and building HATEOAS-driven APIs on the server side. Now, it's time to complete the picture and address the equally important client-side perspective. Building a client for a HATEOAS API isn't just about making HTTP requests. It requires a fundamental shift in how client applications interact with the API, moving from rigidly defined endpoints to dynamically discovered capabilities. The client's mindset shift, from hard-coded to hypermedia-aware. For too long, client developers have been accustomed to hard-coding URLs, assuming their structure, and consulting external documentation to understand workflows. With HATEOAS, this paradigm is turned on its head. The client becomes hypermedia-aware. Instead of, to get a list of products, I'll call get/API/v1/products. To add to cart, I'll call post/API/v1/shopping cart/items with a JSON body. Producted. Quantity. After adding to cart, the user proceeds to checkout. The hypermedia-aware client thinks, from the root, I'll look for a link with rel equals products and follow it. Once I'm at the product resource, I'll look for an add to cart action. The API response will tell me where to send the request, the href, what HTTP method to use, e.g., post, and what fields are required, e.g., producted quantity. After adding to cart, I'll examine the shopping cart resource. If there's a link or action with rel equals checkout, I'll present that option to the user. This shift makes the client more resilient. It becomes flexible, responding to the API's current capabilities rather than breaking when those capabilities evolve. Building hypermedia-aware clients, core principles. Start at a well-known entry point. Every HATEOAS client needs at least one hard-coded URI, the service entry point, e.g/API. From there, everything else is discovered. Generic hypermedia parsers. Instead of custom JSON parsing for every resource type, use or build a generic parser for your chosen hypermedia format, HAL, Siren, etc. This parser should extract the resource's data properties. All embedded links, indexed by their rel, e.g., link self, links next, links customer. All hypermedia controls actions, indexed by their name or rel, e.g., actions add item. Follow links, don't construct URIs. The cardinal rule. When the client needs to navigate to a related resource or perform an action, it must use a link or action provided by the API. Conceptual client-side logic. Assume response is the parsed HAL Siren representation of an order. Const order links equals response links to get customer details. If order links customer, fetch order links customer href. Then res equals res JSON. Then customer data equals console log, customer data, else. Console warn, no customer link found for this order. Semantic interpretation. Clients interact with link rel values, e.g., add item, cancel order. Your client-side code will have logic that says, if I see a link with rel equals add item, then I should enable the add to cart button. The client code still dictates what interface to show, but the API tells it if the underlying action is currently possible. Consuming hypermedia responses in practice. Let's illustrate with our order example. Scenario: a client receives a pending order in HAL format. Order it, ORD123. Status: pending. Total amount, 100.00. Links: self, href, orders ORD123. Add item, href, orders ORD123 items. Cancel, href, orders ORD123 cancel. Confirm, href, orders ORD123 confirm. Client-side reactivity. Function to update UI based on order state. Function render order details, order representation. Const ordered, order representation ordered. Const current status equals order representation status. Const links equals order representation links. Document get element by ID, order ID display. Text content equals ordered. Document get element by ID, status display. Text content equals current status. Dynamically enable disable buttons based on available links. Const add item btn equals document get element by ID add item button. Const cancel btn equals document get element by ID cancel button. Const confirm btn equals document get element by ID confirm button. Const track shipment btn equals document get element by ID track shipment button. Add item btn style display equals links add item. Block none. Cancel btn style display equals links cancel. Block none. Confirm btn style display equals links confirm. Block none. Track shipment btn style display equals links track shipment. Block none will be none for pending. Attach event listeners dynamically. If links add item btn on click equals show add item modal links add item href. If links cancel btn on click equals confirm cancel links cancel href. If links confirm btn on click equals confirm order links confirm href. Example usage: fetch /orders /ord123. Then res JSON. Then render order details. When order state changes after an action, e.g., confirm order, confirm link href. Fetch confirm link href method, post. Then res JSON. Assuming server returns updated order representation. Then order representation equals render order details, order representation. Notice how render order details doesn't hardcode what links should be present for a pending or confirmed status. It simply checks if a link exists and reacts accordingly. This makes the UI adaptive to changes in server-side business logic. Managing hypermedia forms actions. When using formats like Siren, the client can get explicit instructions for performing post, PUT, delete, or patch operations. Scenario: a client receives a Siren order with add item action. Order properties and links, actions. Name, add item. Title, add item to order. Method, post. href, orders ORD when 23 items. Type, application/JSON. Fields, name, producted, type, text, title, product ID. Name, quantity, type. Number, title, quantity, value, 1. Client-side logic for forms. Function to generate a form dynamically. Function create form for action, action. Const form equals document create element form. Form action equals action href. Form method equals action method. Forming type equals action type equals applications/JSON. Applications/JSON. Applications/XWWW form Erlang coded. Action fields for each field equals. Const label equals document create element label. Label text content equals field title field dot name. Form append child label. Const input equals document create element input. Input dot name equals field dot name. Input type equals field type text. Default to text if not specified. If field value equals undefined, input value equals field value. If field required, input required equals true. Add more attributes like min, max, pattern, etc. for client-side validation hints. Form append child input. Form append child document create element br. Const submit btn equals document create element button. Submit btn type equals submit. Submit btn text content equals action title action dot name. Form append child submit btn. Override default form submission to send JSON if needed. Form on submit equals async. Event equals event prevent default. Const form data equals new form data form. Let data equals form data for each. Value key equals data key equals value. Try. Const response equals await fetch action href. Method action method. Headers content type action type. Body JSON stringified data. Const result equals await response JSON. Render order details result. Re-render with new state. Catch error. Console error action failed. Error. Return form. Usage. Const add item action equals order representation actions find. A dot name equals add item. If add item action. Document get element by ID add item form container. Appends child create form for action add item action. This is a powerful pattern. The client can literally generate UI elements and their submission logic based entirely on the API response. This is how web browsers work with HTML forms. They don't know the form details beforehand. They render what the server sends. Leveraging caching mechanisms, HATEOAS and REST are stateless and cacheable by design. Clients should effectively leverage HTTP caching headers, e.g., cache control, etag, last modified, to improve performance and reduce server load. Conditional requests. When an etag or last modified header is present in a resource response, include it in subsequent GET requests for the same resource, if none match, if modified since. If the resource hasn't changed, the server can respond with 304 not modified, saving bandwidth. Cache control directives. The server signals how and if a resource should be cached. Clients should respect these directives. Handling evolution gracefully. The primary benefit of HATEOAS for clients is resilience to change. New links actions. If the server introduces a track gift wrapping link, older clients simply ignore it. Newer clients, once updated to recognize the rel, can seamlessly integrate this new feature without breaking existing functionality. Deprecated links. If a link, e.g., old checkout process, is being deprecated, the server can simply remove it from responses. Clients will no longer see that option. For a transition period, you might decide to return 410 GON if a client tries to use an old hard-coded URL that has been completely removed. URI changes. Since clients follow links by rel and not hard-coded hrefs, If the server changes orders ORD123 cancel to sales transactions ORD123 void, the client doesn't need to change. It simply follows the updated cancel link. Considerations for client-side libraries. While HATEOAS aims for simplicity, building the parsing and dynamic interaction logic from scratch can be tedious. Many SDKs and libraries exist for various programming languages and hypermedia formats that can abstract away the boilerplate. HAL clients often provide methods to conveniently access links, resource-get-link, customer, and embedded resources, resource-get-embedded items. Siren collection plus JSON clients focus more on action form parsing and submission assistance. These libraries simplify the mechanical aspects, allowing client developers to focus on the semantic interpretation and UI presentation. Building a client for a HATEOAS API is a journey of relinquishing explicit control in favor of dynamic discovery. It leads to more flexible, maintainable, and robust client applications that can adapt gracefully to the evolving capabilities of the server, truly embodying the promise of a self-describing and evolvable system. In the next chapter, we'll dive deeper into how HATEOAS enables complex application workflows and how hypermedia forms explicitly guide these state transitions. 8. Navigating workflows. State transitions and forms. We've highlighted how HATEOAS empowers clients to discover what they can do next. This capability goes far beyond simple navigation and data retrieval. It's the core mechanism for guiding client applications through complex, multi-step business processes. This chapter will delve into how HATEOAS explicitly defines and manages application workflows, especially through the use of hypermedia forms. Beyond CRUD, modeling application workflows. Many APIs are designed as simple CRUD, create, read, update, delete interfaces to entities. While this is a common need, real-world business processes are rarely so simplistic. An order might need to be paid for, fulfilled, shipped, and then delivered. A loan application might involve stages like submission, credit check, approval, and disbursement. These are workflows, and the API is the ideal place to communicate the valid transitions within these workflows directly to the client. In a non-HATEOAS API, the client is burdened with knowing the workflow rules. If the order is in pending state, I can post to /orders/ID/confirm or /orders/ID/cancel. If it's confirmed, I can post to /orders/ID/ship. This knowledge is hard-coded, leading to the brittleness we discussed. With HATEOAS, the server explicitly manages the workflow and communicates it through the presence or absence of links and actions. What changes when the state changes? Available actions. A resource in one state will offer different actions than the same resource in another state. Order pending resource might offer cancel order, add item, confirm order links actions. Order confirmed resource no longer offers add item or cancel order. Perhaps cancel order is a different action that involves a refund process, but now offers track shipment, generate invoice. Order shipped resource only offers track shipment and mark delivered. Data representation. While not strictly HATEOAS, the data within the representation might also change slightly as the resource progresses through states, e.g., adding a shipmented or delivery date field. The client's responsibility becomes render data, inspect returned links actions, present UI elements for only the currently available links actions, perform the request as indicated by the link action, representing state transitions. The primary way HATEOAS depicts state transitions is through the strategic inclusion or exclusion of link relations and hypermedia controls. Semantic links are key. The rel of a link, cancel order, confirm order, track shipment directly tells the client the meaning of the transition. Server as the truth source. The server evaluates the current state of a resource and potentially the user's role, as discussed in Chapter 6, and dynamically determines which transitions are valid. It then draws these transitions as links or actions in the response. Example, a payment resource workflow. Consider a payment resource that starts as CREATED, then moves to authorized, captured, and refunded. 1. Payment created. Paymented, pay $7.89. Status created. Links. Self href. Payments pay $7.89. Authorize href. Payments pay $7.89. Authorize. Action. Post to authorize. Client knows it can only authorize. To payment authorized. Paymented. Pay $7.89. Status authorized. Links. Self href. Payments pay $7.89. Capture href. Payments pay $7.89. Capture. Action. Post to capture. Void href. Payments pay $7.89. Void. Action. Post to void. Client now sees options to capture or void. The authorized link is gone. This pattern allows for highly dynamic and resilient workflow management. If a payment gateway adds a new pre-capture step, the server simply returns a new link or action representing that step, and the HATEOAS client, if updated to understand that specific rel, can seamlessly integrate it. Hypermedia forms, enabling user input and complex actions, while a simple post or delete link can represent a state transition, e.g., post orders ORD123 cancel to cancel. Many actions require the client to provide additional data. This is where rich hypermedia forms and actions become essential. As discussed in Chapter 4, formats like Siren excel here. Hypermedia forms allow the server to specify input fields. What data is required, e.g., amount, reason, new status. Indicate data types, hints for UI, e.g., text, number, Boolean, date. Provide default values, pre-populate fields where desirable. Communicate constraints, max length, min-max values, regular expressions patterns, allowed enum values. These act as hints for client-side validation, though server-side validation is always paramount. Define methods and target URIs. Explicitly state the HTTP method, post, PUT, etc., and the exact URI to which the form data should be sent. Example: a refund action for a captured payment using conceptual fields. Paymented, pay $7.89. Status captured. Other links and properties, actions. Name, refund payment. Title, issue refund. Method, post. href, payments pay $7.89 refund. Type, application/JSON. Fields, name, refund amount type, number required. True title, amount to refund min, 0.01 max, 100.00. Name, reason type, text required, false title, reason for refund, placeholder. Optional reason. The client receives this, dynamically renders a form with amount to refund and reason fields, and knows exactly how to submit the data upon user interaction. Prefetching and conditional logic. In some complex workflows, a client might need to decide whether to show a certain UI component or fetch additional data before presenting an action to the user. Prefetching. While the ideal HATEOAS client follows links as needed, for certain high-confidence scenarios, e.g., likely next step in a critical path, a client could prefetch a linked resource to optimize user experience. This must be done carefully to avoid unnecessary requests. Conditional display by rel. The most common conditional logic in HATEOAS clients is simply checking for the presence of a specific link rel. If the rel for refund payment is present, display the refund button, otherwise hide it. This is robust and simple. Implementing idempotent operations. As your API grows and connects to external systems, e.g., payment gateways, ensuring operations are idempotent becomes crucial. An idempotent operation is one that can be safely repeated multiple times without changing the result beyond the initial application. In HATEOAS, get, PUT, delete are inherently idempotent. Post is generally not idempotent. A post to create an order multiple times will create multiple orders. For post operations that initiate processes that should be idempotent, e.g., process order, the server can be designed to use a client-provided idempotency key in the request header. If the server receives the same idempotency key within a certain timeframe, it can ensure the operation is only executed once, returning the result of the original execution for subsequent identical requests. This is a common pattern in payment processing APIs. The hypermedia action might reflect this by providing a field for the idempotency key or the client is simply expected to add it to the request. Handling concurrency. Optimistic locking via e-tags. In distributed systems, multiple clients might try to modify the same resource simultaneously. Optimistic locking helps prevent lost updates. E-tag header. When a resource is first retrieved via GET, the server should include an e-tag, entity tag, HTTP header in the response. This e-tag is usually a hash of the resource's current representation. Conditional updates. When a client wants to put or patch that resource, it includes the e-tag it received in an if-match header in its request. Server check. The server then compares the e-tag in the if-match header with the e-tag of the resource's current state. If they match, the update proceeds. If they don't match, meaning another client modified the resource since this client retrieved it, the server returns a 412 precondition failed error. The client can then decide to reload the resource, present the user with the conflict, or retry the operation. While not strictly a HATEOAS construct, e-tags are a standard HTTP mechanism that meshes perfectly with the hypermedia approach to build robust, concurrent systems. By explicitly designing workflows into your API's hypermedia, defining clear state transitions, and using hypermedia forms to collect input, you empower your client applications to be remarkably agile and resilient. The server becomes the central intelligence for guiding client interactions, leading to more robust and maintainable overall systems. Next, we will cover how to ensure these sophisticated HATEOAS APIs are well-tested and clearly documented. 9. Testing and documenting HATEOAS APIs. Building a HATEOAS-driven API is a significant architectural decision that impacts both server and client development. To ensure its stability and usability, effective testing and clear documentation are paramount. However, traditional API testing and documentation approaches often fall short for HATEOAS, as they tend to focus on static endpoints rather than dynamic link-driven interactions. The challenge of testing HATEOAS APIs. Most common API tests are integration tests that directly call fixed URLs. For example, get/API/v1/users/AD or post/API/v1/orders. This works well for non-HATEOAS APIs, but directly contradicts the core tenet of HATEOAS. Clients discover and follow links, they don't hardcode URLs. If your tests hardcode URLs, you're not truly testing the HATEOAS nature of your API. You're just testing the underlying data and HTTP methods. This means future URI changes, which HATEOAS is designed to gracefully handle, might still break your tests, even if they wouldn't break a HATEOAS client. Designing HATEOAS-ware tests. The key is to make your tests behave like a HATEOAS client, driven by links, not hard-coded paths. Test the entry point. Your test suite should begin by hitting the API's designated entry point, e.g., /API. This is the only hard-coded URL a HATEOAS client needs. Focus on link relations, rels, not URIs. Instead of asserting response URL == orders 123 cancel, assert that the response contains a link with rel = cancel. Test that links are present when they should be and absent when they shouldn't, e.g., a cancel link for a pending order but not for a shipped order. Simulate client navigation. Your tests should traverse the API by following links. Conceptual test scenario, order workflow. Test, user can place, confirm, and track an order, async, equals. 1 start at entry point, hard-coded once. Const API root = await get, /API. Assume a test helper get fetches and parses, HATEOAS. Expect API root has link orders collection to be true. 2 navigate to orders collection. Const orders collection = await get, API root get link orders collection. href. Expect orders collection has action place order to be true. 3 place a new order using the discovered action. Const place order action = orders collection get action place order. Const new order = await post place order action href place order action method producted. P101 quantity 1 expect new order properties status to be pending. Expect new order has link self to be true. Expect new order has link confirm order To be true, expect new order has link cancel order. To be true. 4. Confirm the order. Const confirmed order equals await post, new order get link, confirm order. href. Expect confirmed order dot properties status. To be confirmed, expect confirmed order has link confirm order. To be false. Verify link is gone. Expect confirmed order has link track shipment. To be true. 5. Track the shipment. Const shipment equals await get confirmed order get link track shipment. href. Expect shipment dot properties status to be in transit, and so on. This approach validates correct link generation, that the server is exposing the right links at the right time. Workflow adherence, that the API guides the client through valid state transitions. Resilience to URI changes. If orders confirm changes to order processing confirm, the test won't break as long as the server correctly returns confirm order link. Test hypermedia controls forms. Assert that actions are present when they should be. Validate the structure of actions, fields, method, href. Submit data according to the action's definition and verify the outcome. Contract testing for hypermedia. For large systems with many independent clients and servers, consider contract testing. This involves consumer-driven contracts. The client-consumer defines the exact links and actions it expects from the server provider. Verification. These contracts are then run against the server's API to ensure compliance. Tools like Pact or Spring Cloud Contract can be adapted for HATEOAS by focusing assertions on link relations rather than concrete paths. Documenting HATEOAS APIs. Traditional API documentation focuses on listing endpoints, their parameters, and expected responses. For HATEOAS, this is insufficient because the API's behavior is dynamic. Documentation must describe the semantics of link relations and the states of resources, along with the hypermedia controls available in those states. Start with the entry point. Clearly document the API's single or few public entry points. Document resource states and transitions. For each major resource, e.g., order payment, describe its possible states, e.g., pending, confirmed, shipped. For each state list, the expected data properties. All available links by rel and their href URI template if applicable. All available actions hypermedia controls by name or rel, including their HTTP method, target URI, and required input fields. Crucially, explain what each link action means semantically. Provide a state machine or workflow diagram. Visually represent the lifecycle of a resource, showing states as nodes and links actions as directed edges between them. This is exceptionally helpful for understanding the API's overall behavior. Example, simplified order lifecycle. Pending confirm order confirmed. Pending cancel order canceled. Confirmed track shipment shipped. Define custom link relations. Maintain a glossary or registry of all your custom link relations. For each, provide a clear, concise definition of its semantic meaning. Indicate what resource types it applies to. List which HTTP methods it typically implies, e.g., place order implies post. Document hypermedia forms actions. For each action, name title, purpose description. HTTP method. Target URI can be template. Details of all input fields. Name, type, description, required, validation rules, min-max, regex, enum, and examples. Interactive documentation. Static documentation is good, but interactive documentation is better. Consider tools that allow developers to explore your API by browsing, clicking links and seeing the resulting responses, like a mini browser. Executing actions, submitting test data to hypermedia forms. While OpenAPI, Swagger, is fantastic for describing the data structures and operations, it doesn't natively represent HATEOAS link relations and state transitions dynamically. You might need to augment OpenAPI definitions with custom fields or rely on a combination of tools. OpenAPI for data and a separate, human-readable guide for the hypermedia aspects. Alternatively, specialized HATEOAS documentation frameworks, which are less common than OpenAPI tools, might emerge or evolve to support this dynamic nature more directly. The importance of relation documentation. The most critical part of HATEOAS documentation is the clear, unambiguous definition of your link relations. This is the contract that the API uses to guide client behavior. If rel equals pay means make a full payment in one context and make a partial payment in another, clients will be confused, and the benefits of HATEOAS will be lost. By rigorously testing your API's HATEOAS aspects and providing thorough, hypermedia-aware documentation, you ensure that your API is not just evolvable on the server side, but also understandable and consumable by its clients. This reduces the friction of adoption and maximizes the return on your investment in HATEOAS. In the next chapter, we'll explore some advanced scenarios and considerations for integrating HATEOAS into more complex system architectures. 10. Advanced HATEOAS scenarios and considerations. We've covered the fundamental principles, design, implementation, testing, and documentation of HATEOAS APIs. Now, let's explore some more advanced topics and real-world considerations that arise when integrating HATEOAS into complex systems. These scenarios often involve balancing pure hypermedia principles with practical system requirements. Authentication and authorization in a HATEOAS context. Security is paramount for any API. In a HATEOAS environment, security becomes even more dynamic. Not only do you control who can access a resource, but also what actions they can perform on it, expressed through the links and actions presented. Conditional link exposure. Based on the authenticated user's roles and permissions, the server should dynamically include or exclude specific links and actions in the response. Example: an administrator viewing a user resource might see deactivate user and reset password links, while a regular user viewing their own profile only sees edit profile and change password. This is the security mechanism by which discoverability inherently aids authorization. If a user isn't allowed to cancel order, then the cancel order link simply won't appear in the response to their request. The client doesn't need to implement separate permission checks. It renders only the actions provided by the server. Integration with identity providers. Standard authentication mechanisms like OAuth 2.0 or OpenID Connect fit seamlessly. The client authenticates with the identity provider, e.g., Auth0, Okta, Keycloak, to obtain an access token. This token is then included in the authorization header of all subsequent requests to the HATEOAS API. The API server validates the token and uses the embedded claims, e.g., user ID, roles, scopes, to determine which links and actions to include in the hypermedia response. Versioning HATEOAS APIs. Traditional API versioning, v1, v2, is often a pain point. HATEOAS offers a more elegant approach to evolution, minimizing the need for explicit versioning in many cases. Prefer evolution over explicit versioning. The ideal HATEOAS API evolves gracefully. New resources links. If new functionality is added, the server simply returns new links with new rel values where appropriate. Older clients that don't understand the new rel values will ignore them, continuing to function without breaking. Changing URIs. As established, if a URI changes but its semantic rel remains stable, clients continue to follow the link without needing updates. Optional fields. Adding new optional fields to existing representations generally doesn't break old clients, they just ignore the new fields. Deprecating links actions. To phase out old functionality, the server simply stops providing the old link action. Clients will no longer see that option. For a transition period, if a client tries to use a deprecated operation, perhaps it's hard-coded for historical reasons, or it's an old client that somehow stored the href persistently. The server can return a 410 gone status code or a 404 not found with a helpful error message and a link to a resource explaining the deprecation, when true versioning might still be necessary. While HATEOAS minimizes breaking changes, it doesn't eliminate all needs for explicit versioning. Consider explicit versioning when fundamental semantic changes. The meaning of a core link relation fundamentally changes, or critical fields are removed renamed in a way that would break existing clients even with dynamic discovery. Major architectural overhauls. a complete reimagining of a major part of your domain. Client migration strategy, if you have many external clients that you need to explicitly migrate over time. Even in these cases, try to keep the versioning granular, e.g., version a specific resource or a logical API boundary like account v2, rather than impacting the entire API. And strive for minimal overlap. Pagination and filtering. Large collections of resources need pagination and filtering. HATEOAS handles this naturally. Pagination links, when returning a collection, include standard next, prev first, last links in the response. These links can either contain query parameters, e.g., /products, page equals 2 and size equals 10, or be full HATEOAS links to the next result set. Collection /items. Links, self, href, /products, page equals 1 and size equals 10. Next, href, /products, page equals 2 and size equals 10. Last, href, /products, page equals 10 and size equals 10. Filtering sorting links. You can provide HATEOAS links that describe filtering or sorting options. These are often URI templates. Links, search products, href, /products category min price max price, templated, true. Sort by name, href, /products sort equals name, templated, false. Or, as seen with collection plus JSON, explicitly provide queries fields that clients can fill out dynamically. Asynchronous operations. Some operations take a long time to complete, e.g., video encoding, large data import. Directly blocking the client with a synchronous request isn't ideal. HATEOAS can represent asynchronous workflows. Immediate acknowledgement. When a client initiates a long-running task, the server immediately returns a 202 accepted status code, or 200 OK, with a response that includes a link to a job status or task status resource, rel equals status or rel equals monitor. Optionally, a link to a result resource, rel equals result, which would only become active once the job is complete. Jobid, job 456. Message, processing request asynchronously. Links, self, href, jobs job 456. Status, href, jobs job 456, same as self for status updates. Cancel job, href, jobs job 456 cancel. Polling. The client can then periodically poll the status link until the job is complete. The job status resource itself should also be HATEOAS-driven, changing its links as the job progresses, e.g., from in progress to completed, and then fetch results. Semantic web and linked data. HATEOAS, at its philosophical root, shares common ground with the semantic web and linked data principles. Linked data principles. Use URIs as names for things. Use HTTP URIs so that people can look up those names. When someone looks up a URI, provide useful information using standard formats. Include links to other URIs so they can discover more things. HATEOAS directly implements principles 2, 3, and 4 shared vocabularies. While HATEOAS doesn't mandate specific ontologies, the use of IANA link relations and the disciplined use of custom link relations contributes to building a shared vocabulary, aiding machine readability and interoperability. For truly advanced scenarios where machine agents need to understand the meaning of data beyond simple rel definitions, incorporating richer semantic annotations, e.g., using JSONLD for schema.org data, could be combined with HATEOAS. Content negotiation. Your HATEOAS API might need to support multiple hypermedia formats or different media types for representations, e.g., application/HAL plus JSON or application/Siren plus JSON. REST-S uniformity constraint implies that clients should use content negotiation to request their preferred format. Accept header. Clients include an accept header in their request, e.g., accept application/HAL plus JSON. Content type header. The server responds with the content type header indicating the format it is returning, e.g., content type, application/HAL plus JSON. Media type profile parameter. Some specifications, like HAL, allow for a profile parameter in the content type header to denote a specific format. For example, content type, Application/HAL plus JSON. Profile equals http example.org/profiles/order-profile. This can further constrain the semantics of the response. Supporting content negotiation allows your API to serve different types of clients with their preferred hypermedia representation without changing the URI. These advanced considerations demonstrate that HATEOAS is not just a theoretical concept, but a robust architectural style that can be applied to solve complex problems in distributed systems. It promotes flexibility, resilience, and better maintainability. In the next chapter, we will consolidate this knowledge by examining real-world applications and specific case studies where HATEOAS has made a tangible difference. 11. Real-world applications and case studies. Theory is essential, but seeing how HATEOAS plays out in practical scenarios truly solidifies its value. While public-facing APIs heavily leveraging HATEOAS are somewhat rare, primarily because public API consumers, developers, often prefer the predictability of static documentation and the flexibility of composing URLs themselves, HATEOAS shines in particular domains and internal systems where its benefits are highly impactful. Let's explore a few conceptual case studies and discuss where HATEOAS makes a significant difference. Case Study 1, E-commerce platform, the adaptive checkout flow. Problem: a traditional e-commerce API often has a fixed, hard-coded checkout flow. If the business introduces a new payment method, a different shipping option, or a dynamic discount system, all client applications, web, mobile, third-party integrations, need to be updated and redeployed. This leads to high maintenance costs and slow feature rollout. HATEOAS solution: the API response for a shopping cart resource or a checkout session resource is rich in hypermedia. Initial cart state: a GET cart response might initially show items, subtotal, and links like apply coupon, select shipping address options, start checkout. If the cart value is below a minimum, the start checkout link might be absent. Applying a coupon, the apply coupon link action is followed. The server processes the coupon and returns an updated cart representation. This new representation automatically includes a discount applied property, updated total amount, conditional links. If the coupon offers free shipping, the select shipping method link might disappear for free options, or a shipping method selected link with a pre-selected free option might appear. Dynamic payment methods: when the client follows the start checkout link, the response for a checkout session includes the href for submit payment, a list of available payment method links, e.g., PayPal checkout, Stripe credit card, bank transfer. Each payment method link carries information about required input fields via hypermedia forms, e.g., for Stripe, card number, expiry date, CVV. Crucially, the API can dynamically filter payment options based on user location, total order amount, e.g., enable installments for large orders, products in cart, e.g., certain products can't be paid via certain methods, customer history, e.g., enable buy now, pay later for trusted customers. Benefits: reduced client deployments. The client doesn't need to know the business logic behind which payment methods are available or which steps are next. It simply renders the UI based on the links and actions provided by the API. New payment methods or shipping rules can be added on the server side without touching client code. Flexibility and agility. The e-commerce platform can quickly adapt to new business requirements without a costly, synchronized client-server rollout. Improved user experience. The checkout flow seamlessly guides the user through available, valid options, minimizing errors. Case Study 2. Workflow automation in enterprise systems, e.g., loan origination. Problem: enterprise applications often manage highly complex, multi-stage business processes. For example, a loan application goes through dozens of steps: application submission, document upload, credit check, underwriting, approval, disbursement, and possibly rejections at various stages. Traditional APIs would require the client to hardcode the entire state machine, making changes prohibitively expensive. HATEOAS solution: the API manages the loan application resource. Each stage of the application lifecycle is represented as a state, e.g., initialized, PNDNGDOCUMENTS, CREDIEREVIW, approved, rejected. Initial application creation. A post to applications returns an application resource in initialized status, with links like upload documents, edit applicant details. Document upload pending. Once documents are uploaded, the application moves to PNDNGDOCUMENTS. The API response might now include links for submit for review, if all documents are present, or request additional documents, if certain documents are missing, and cancel application. The upload documents action could even specify a list of expected document types, e.g., passport, bank statement, as fields in the hypermedia form. Underwriter review. When the application is in CREDIEREVIW, the API exposes different actions links based on the underwriter's permissions. Approve application, request more information, escalate to senior underwriter, reject application. Benefits. Centralized business logic. All workflow rules reside on the server. The client is merely an intelligent renderer. Reduced development cost. Clients don't need to be tightly coupled to workflow logic, reducing the complexity of client-side development and maintenance. Auditable and enforceable workflows. The API ensures that only valid state transitions occur, improving data integrity and compliance. Adaptability to regulatory changes. If a new step or a new approval is required due to regulatory changes, it can be introduced in the API, and clients will automatically adapt. Case Study 3. Internal Microservices Communication. Problem: in a microservices architecture, services often interact with each other via internal APIs. If Service A hardcodes the URLs and request bodies for Service B, any change in Service B's internal structure, e.g., a reorganization of resources, a new intermediate step in a process, requires coordinating changes across multiple services. This tightly couples the services, defeating part of the microservices promise. HATEOAS solution. Internal service APIs also embrace HATEOAS. Service discovery. Service A might initially find Service B via a service registry. Once found, Service B's root URI/Service B API becomes the entry point. Inter-service workflow. If Service A needs to initiate a complex process in Service B, e.g., process order fulfillment, Service A requests /Service B API/fulfillments. Service B responds with a fulfillment resource and an initiate fulfillment action, specifying required input parameters. Service A follows this action, and Service B, based on the fulfillment state, returns a fulfillment resource with dynamic links for track status, cancel fulfillment request, etc. Benefits: looser coupling. Services are loosely coupled. Service A doesn't need to know Service B's internal URI scheme or exact workflow steps, only the meaning of the link relations. Improved resiliency. Changes within Service B, e.g., adding an internal validation step, splitting a resource, don't break Service A as long as the link relations remain consistent. Independent evolution. Teams owning different microservices can evolve their APIs more independently. HATEOAS in public APIs and its nuances. While the benefits within internal systems and B2B integrations are clear, truly HATEOAS-driven public APIs, where developers are the primary consumers, are less common. Why? Developer preference. Many developers prefer static documentation, like Open API Swagger, and direct, predictable endpoint. The cognitive overhead of dynamically parsing and iterating through hypermedia for every operation can seem higher than simply looking up an endpoint in docs. Tooling maturity. While clients for hypermedia are improving, the ecosystem for public API development, e.g., code generation from Open API specs, is more mature for static, endpoint-based APIs. Scope: public APIs often offer broad access to data, where the concern is more about data structure and schema, and less about guiding complex, predefined workflows. However, HATEOAS principles do appear in parts of many successful public APIs, e.g., pagination links, related resource links. For APIs that truly require workflow guidance and robust evolvability over time, especially for long-lived systems with multiple client types, HATEOAS remains the architectural North Star. These case studies underscore that HATEOAS isn't just about elegant API design. It's about solving concrete business challenges related to system flexibility, maintainability, and responsiveness to change. By choosing HATEOAS where it truly offers value, you can build systems that gracefully adapt and thrive in an ever-evolving digital landscape. In our final chapter, we'll cast an eye to the future of API design and the enduring significance of embracing evolvable systems. 12. The future of API design. Embracing evolvable systems. We have journeyed through the intricate landscape of HATEOAS-driven REST APIs, starting from the foundational principles of REST, dissecting the challenges of traditional API evolution, and exploring the detailed mechanics of designing, implementing, testing, and consuming hypermedia-rich responses. We've seen how HATEOAS transforms APIs from mere data endpoints into sophisticated engines guiding application state. Now, it's time to reflect on the broader implications of this architectural style and its enduring relevance in the rapidly evolving world of API design. The enduring value of HATEOAS. In a software landscape often characterized by rapidly changing technologies and architectural fads, HATEOAS represents a fundamental principle that transcends specific technologies. It's not about JSON or XML. It's about breaking the intimate coupling between clients and servers. It's about designing systems that can adapt and evolve without constant, disruptive coordination between producers and consumers. The core promise of HATEOAS, that an API's capabilities and workflows are discovered at runtime rather than being hard-coded, addresses a perennial problem in distributed systems: brittleness and high maintenance costs due to tight coupling. As systems grow larger, more complex, and more interconnected, especially with the rise of microservices and serverless architectures, the ability for components to evolve independently becomes increasingly vital. HATEOAS provides a robust mechanism for achieving this independence. Beyond REST, Graph APIs, GraphQL, and hybrid approaches. It's natural to consider HATEOAS in the context of emerging API paradigms, especially GraphQL, which has gained significant traction. GraphQL offers powerful features for querying exactly the data a client needs, reducing overfetching and underfetching. However, GraphQL and HATEOAS solve different problems. GraphQL excels at data fetching and aggregation. It simplifies data access by allowing clients to specify their data requirements declaratively. It's primarily about efficient data retrieval. HATEOAS excels at guiding application workflows and enabling API evolution. It's about communicating available actions and state transitions. Can they coexist? Yes. A GraphQL API could provide the initial data payload for a resource, and that resource's representation could include hypermedia links for actions or workflows that cannot be succinctly described or initiated purely through data queries. For example, a GraphQL query might fetch all details of an order, and within that order, a HAL links object could provide the cancel order or track shipment URIs and associated metadata. It's a better together scenario for specific use cases. For internal, complex, state-driven business processes, a hybrid approach leveraging the best of both worlds might emerge, where GraphQL provides data flexibility and HATEOAS handles workflow navigability. Artificial intelligence and machine learning with HATEOAS. Looking further into the future, HATEOAS holds significant potential for enabling truly autonomous software agents. Imagine a scenario where an AI or ML system needs to interact with various web services to accomplish a complex task. Say, finding the best route while optimizing for weather conditions, traffic, sustainability, and personal preferences across multiple third-party transportation providers. Without HATEOAS, the AI would need pre-programmed knowledge of every API's endpoint structure, input parameters, and workflow semantics. This is brittle and scales poorly. With HATEOAS, an intelligent agent could start at a route URI, identify a find route link, explore its available parameters, and then dynamically discover steps like select transport mode and book ticket. adapting to each provider's unique workflow purely through the hypermedia. This concept extends to enabling headless commerce or headless services, where software clients can act as primary consumers of complex services, interpreting hypermedia and making decisions automatically. The self-describing nature of HATEOAS could be key to building a truly adaptive web of services, where machine intelligence can navigate and integrate more autonomously. The paradigm shift from integrating with an API to navigating an application state via an API. The journey of understanding HATEOAS is fundamentally a shift in mindset. It moves us away from viewing an API as a collection of static data endpoints that we interact with using external documentation. Instead, it encourages us to see the API as a living, breathing application whose state and capabilities are dynamically communicated to its consumers. This means, for API providers, a greater responsibility to correctly model application state and to provide meaningful link relations and hypermedia controls. This requires a deeper understanding of the business domain and its workflows. For API consumers, a need to write more adaptive and flexible client code that can parse and react to hypermedia. This often involves embracing generic client patterns and semantic interpretation over rigid, hard-coded logic. Final thoughts on adoption. Despite its significant architectural advantages, HATEOAS has not seen universal adoption. The perceived complexity of implementation, particularly on the client side, and the lack of robust, developer-friendly tooling specific to HATEOAS, compared to, say, OpenAPI for endpoint-based APIs, have been barriers. However, for internal APIs, B2B integrations, and systems with long life cycles where evolvability is critical, the investment in HATEOAS pays dividends in terms of reduced maintenance costs, fewer breaking changes, less client-server coordination, increased agility, faster independent evolution of services and clients, enhanced reliability, systems that adapt gracefully to changes, cleaner separation of concerns, business logic belongs on the server, UI presentation on the client. Embracing HATEOAS requires thoughtful design, a commitment to consistent link relations, and a willingness to challenge conventional API consumption patterns. It's an investment in the long-term health and adaptability of your software ecosystem. Call to action. The principles underlying HATEOAS are timeless and foundational to truly distributed systems. While the specific technologies and formats may evolve, the idea of an API being its own documentation, dynamically guiding its consumers, remains a powerful vision. We encourage you to experiment. Begin implementing HATEOAS in a small, contained internal project. Educate, share the benefits and principles with your teams. Advocate, champion evolvable API design in your organization. Building evolvable systems is not a luxury. It's a necessity in today's rapid-paced digital world. By incorporating the wisdom of HATEOAS, you are not just building better APIs. You are building a more resilient, adaptive, and future-proof software landscape. Suggested further reading: Roy Fielding's dissertation, Architectural Styles and the Design of Network-Based Software Architectures, Chapter 5 on REST, the foundational text. IANA Link Relation Registry, the authoritative source for standard link relations. Specifications for hypermedia formats, HAL, Siren, Collection plus JSON, Mason deep dives into their structures. Articles and blogs. Many thought leaders in the API space, e.g., Mike Amundsen, Steve Klabnik, have written extensively on HATEOAS and related topics. Books on API design. Explore broader API design principles that pair well with HATEOAS.